In case you guys haven't noticed, there's a bunch of TAs in the room from Databricks, and so if you're running into any problems, just raise your hand, and folks will come help you out.
Okay, so we're still getting set up. I saw there's still some more people checking in. We're getting this going. I've been wandering around. Other folks are, we've got, I don't know, about 5 or 6 of us here who are wandering around to help out. If you're having any troubles getting set up, raise your hand. We'll come help out. The main thing is just to get these green USB sticks, copy them over onto your local drive, onto your desktop, and work from that copy. You don't need to install anything else, really. Also, the slides are up here, the URL for the slides. If you're having any troubles downloading slides, let me know. We can grab those off USB sticks as well. But hopefully the network is happy these days. Anybody having troubles with network, actually? No? Okay. Good. Are we good? Alrighty. I think we're ready to get started then. Okay, we'll get everybody in. I can imagine some folks are out getting coffee. You know, there's plenty of coffee in the next room, and there's also this advanced course that's out beyond the coffee. So we're going to get started here on the intro course. My name is Paco, and we've got a number of other folks here from Databricks and AmpLab. If you could raise your hands right now. Be people helping out throughout the course, especially as we're getting started on this. So welcome to Intro to Apache Spark. We've been touring around the country doing this course, this content, so very grateful to be here at Spark Summit doing it. And this is arguably the largest class that we've had for it so far, so that's great. We've got really 3 items of business, just to make sure everybody's connected to network. Anybody having troubles with network still? Okay, that's great. That's best news I've had all day. And then secondly, we've got a download for the slides. It's probably best to have a copy of slides locally because I'll be bouncing back and forth between browser windows and terminal windows and things like that. And the slides will have most all of what you need to cut and paste or various URLs, etc. So definitely recommend downloading those. And is that working out okay? Anybody having troubles getting to the slides? I think Amazon has been delivering this off the CDN pretty well today. And then, of course, we've got the USB sticks. So for anybody coming in just now, we've had these green USB sticks, little custom Databricks logo. Just copy all the contents there onto a folder on your desktop, onto your local drive, and we'll work from the copy. I feel that that's the easiest way to go. So as far as this course here, okay, well, we've got a couple other URLs. There's a course survey. I'll have this at the end, but it's it's linked at both the front and the end of the content, and definitely want to get feedback. We're building up this program. We've had the Spark Camp, AMP Camp going for a while, but this newer material from Databricks is intended to be a sequence, a multi-course sequence leading to certification. So this is the introductory course. We're thinking we'll probably have another 3-4 courses added on along with this, and then have a developer certification program as a capstone at the end of that. So to get going on that, we really need feedback. We'd like to hear what directions to go with courses, any feedback or suggestions about this course, but certainly the follow-on courses. You know, we're thinking about doing one geared more towards application developers, another geared more towards data scientists, and another geared more towards, say, DevOps. So if there's anything else you'd like to see or particular directions there, we're very eager to hear. And the course survey is probably one of the best places. Certainly contact me, contact me on LinkedIn or send us feedback on Databricks as well. As far as the goals for today, this is the intro course, and this is really meant to help you get started setting up the environment on your laptop. Again, what we've done with the USB sticks. But getting that going, getting that configured, and then begin to work from the REPL. Be able to work from the prompt to write Spark apps in, we'll show both Scala and Python as well as some Java. I'll be switching back and forth between those languages. So as long as you've got some background working in Python, Scala, or Java, and you've got your laptop set up, a lot of this will be cut and paste. If you've already done a lot of Spark programming and you're familiar with this and you want to get more of a deep dive, by all means, I recommend the advanced course. I just want to level set about that this is the intro course. And certainly, if you want to go back and forth, I don't think we've said this before, but a number of people have been asking if you want to be in the intro course, but then catch some of the material in the advanced course. As long as there's seats open there, I'm all for it, so certainly feel free. We're also going to look through more of the API as well in this course. Not a real deep dive, but we'll go through much of the API, show the resources that are available, show some sample code that illustrates a lot of usage of Spark, different parts of the API. We'll get into how to build standalone apps, and from that look at some use cases for, say, machine learning algorithms. Later on, I'm going to fire up a cluster, a Spark cluster in Amazon, and we'll show working with data sets that are in HDFS. Just basically show what's the difference between working on a laptop versus working on a cluster. I'm not expecting that everybody fires up a cluster, most certainly. I'll just do some demos on that. But if you have an AWS account, you want to follow along, certainly. Also, we're going to go through a lot of the features that have come out from Spark 1.0 as far as Spark SQL and be working with examples of that. Also, there's an example of Spark streaming, so I'll hopefully get everybody set up on that, or most people set up. And there's a few advanced topics that we'll cover a little bit later on, not in too much detail, but hopefully give some pointers. Also, there's a number of case studies that I've been trying to put together for this course, and try and review those a bit, give some other pointers to resources. So that's basically the content throughout the day. This is a full-day course. It'll run till 5 p.m., but we'll take a nice break mid-morning, and then, of course, lunch, and in the afternoon. I generally say in the courses, usually we're running courses that are about 30 people, generally say, stop, ask questions. Given the size of this course here, it's probably better to raise your hand if you have any issue. Somebody will come over and try to troubleshoot. But I do like to get a lot of questions in this course. I think that that dialogue is very important. And we've had a lot of fun outcomes based on the dialogue in the previous courses. So I definitely recommend just stop me at any point if you do have questions. I'd love to try to handle that, or somebody else here can help out. Okay, any questions about the content? Good. If there are any, all right, so in the smaller settings, of course, we'll do introductions around the room. I think we'll probably skip that one here. But I'd love to hear more about your use cases, so I'll be cycling around, and certainly during the breaks, I love to hear that. If there are any problems as far as getting laptops going, we do know some edge cases, say if you have Windows and Java 8 and HTTP 2.1 I've seen things like that that are just kind of edge cases we're still trying to figure out. Generally speaking, if you have Windows or Mac or Linux on a laptop, this material should work fine. But if there is a showstopper, we can fire up some AWS nodes, and then you can just SSH into those. Parviz and some others will help out as far as getting that set up if you need it. So far, it doesn't sound like that's the case. Okay, so without further ado, first up, we're going to show in just a few steps, 4 easy steps, how to get started with the REPL, how to write Spark code. So, I usually say go to spark.apache.org and get the latest, download it. In this case, it's already on the USB sticks. So if you've copied that over onto your desktop, you can work from that copy on your local drive. And the other dependency is you do need to have JDK. And so we're recommending JDK 6 or 7, tends to work best. Frankly, I don't have a lot of hands-on with JDK 8 yet. But I'm curious, how many folks are working with JDK 8, Java 8? Okay, good stuff. If there's any issues, let us know. But so far, so good. We're working with Spark 1.00. Actually, what you have on the USB sticks is slightly modified beyond that. But for all intents and purposes, what we're showing here is 1.00. So that's the latest. So to get started on this, the first thing you need to get into the REPL is to run under the bin directory, under the Spark directory, under the bin directory. There's a script called Spark Shell. If you're on Windows, this will be sparkshell.command. But if you run that, let me switch over here. Bin Spark Shell. Alrighty. So if you run /bin/spark-shell, then it'll start this up. You'll get some commands on the console, some logs coming out on the console. But then eventually you should be able to get a Scala prompt. So you see right here in the mid-screen where it says Scala. And from that prompt, that's what we'll be working, entering in commands. If there's any problems as far as setup, they'll probably show up right now. So anybody having issues, any issues on laptops getting this set up? Okay, we'll get people, there's a couple back there. We call this a REPL. It's a prompt. You can type commands and get some kind of response back. As far as Spark is concerned, it's almost as if it's reading through a source file. It has a notion of command lines, line numbers based off of what you're typing on the command line. But let me just make sure. Is this working out okay for everybody? Any other issues? Good stuff. Okay, so first off, we'll try creating some data. So from the REPL, just type in or cut and paste val data equals 1 to 10,000. And this is actually Scala. It's creating a collection of integers from 1 to 10,000. Okay, questions up here? So if this works well, it should come back showing that it's got Scala collection immutable range, inclusive, and then it's got the range of numbers, integers from 1 to 10,000. And thankfully, it doesn't print out all 10,000 of them. This really hasn't invoked Spark yet. This is just inside of Scala creating a collection. Is that working out okay? Or rather, if it's not, let us know. Now, next up, this is where the Spark part comes in. We're going to create an RDD. We'll drill down into the notion of an RDD in much more detail later on. But for right now, we'll just create one. And the way I do that is say val distdata equals sc.parallelize data. So to break that down a bit, we had created this variable data, the integers from 1 to 10,000. And we're using a special variable here called sc, which is our Spark context. And that's created when Spark Shell launches. So we call the API from that. We say sc.parallelize, basically parallelizing this collection of 10,000 integers to create a resilient distributed data set, an RDD. And we save that as a variable. Actually, one question I should have is, can everybody read the font size and the colors and whatnot? In the back of the room, is my terminal window readable? Okay, great. If there's any issues, let us know. I can play around with this. I tend to use yellow on purple, just my eyes are kind of weird. I don't know. If it's hard to read up there, let me know. We actually didn't have the red coming through here earlier, so I guess as long as the projector holds up, that'll be good. All right, so now we've got an RDD. Let's go ahead and apply, let's use Spark. We'll apply a filter to select out the values less than 10. So we're going to call from distData, our RDD, we'll call the filter function. And then inside of that, there's a closure. We have some business logic inside of that. Let me show. So we've got the RDD, distData. We're calling the filter function. Inside of the closure there for the filter function, we've got some business logic that says underscore, which says basically for each element in this RDD, keep the ones that are less than 10. So that expression there inside the closure is a Boolean. It's going to evaluate to true or false for each different element, and the ones that are true will be kept in the filter. And then from there, we call another function, collect. So we're issuing this command, and then we're going to collect the result set back and print that out at the prompt, at the REPL. And so, you know, it comes back with an array of 1 to 9, all the integers less than 10. Is that working okay for everybody? All right. If there's any issues, again, at this point, there may be some things that come up, like for instance, you might see not able to bind to address if you have 2 of these shells running at one time. Just want to try to troubleshoot some of that. Okay. Alrighty. What do you get for results? The results should be 1 to 9. So that's the Spark program. Going back here, I mean, this is the flavor of what we're going to be doing throughout the work today with Spark, is creating an RDD and applying some kind of functions to it, having this business logic inside of your closures. Again, we'll be drilling down into all of this in much more detail in terms of RDDs and Spark context, but this is really the flavor of programming. And here, this is in Scala. We'll show a similar thing in Spark. In Python. And also, speaking of Python, if you do want to work in Python and you don't have Python already installed, I would highly recommend there's Anaconda from Continuum. If there's any troubles downloading that, we can pass this around in USB sticks already. But if you prefer to work in Python, I think that Anaconda is a pretty good, really good package manager. It's what I use. It makes it much easier to control installing and managing Python. On the other hand, if you want to be working in Java, we'll show some Java builds later on. If you want to work in Java and you don't already have Maven, we've got the link there for the download for Maven. If you're not working in Java and you don't have background working with Maven, just skip this part. This is optional. But I just want to make sure that all the dependencies are accounted for. Okay, so let's spend a few minutes talking about Scala. And I'll show some examples here and try to break down some of the elements of what we're using out of the Scala language, and hopefully translate that into more of a Python or a Java context as well. And as well, this example will show what's really happening under the hood in terms of Spark, what's happening across a cluster if you're running on a cluster. So we've got a fairly concise example here of some kind of log file processing. Let's say that you have a bunch of web server logs that have been collected over time, and you've got those in HDFS. So the first line here is what we would call a base RDD. We'll use the SC variable. So we use sc.text file to load in a whole bunch of log files from HDFS. And just for the purposes of example, I'm not going to execute this code here. I'll show some very similar code later on. But just to break it down, you're pointing to the HDFS files, the log files, by using that URL, HDFS:// etc. So we load in some log files, and that creates an RDD. We call that lines. So once we've got this variable lines, or value in Scala, then we're going to apply some transformations to it. So we'll have some transformed RDDs that come out. And a little bit later on, we've got a cache, and then we take some actions and start getting some data back. Now, an interesting thing is that this doesn't all happen at once. And in fact, nothing really happens until we start getting down to the actions at the bottom. And we'll go into that notion of lazy evaluation on the graph a little bit later. But this is a pretty typical kind of app that you would just take a bunch of log files, peel out the errors, and then count up the number of errors, say in MySQL versus PHP. I don't know, this might be going into a dashboard somewhere. So to take a look at this step by step, assume that we're running on a cluster. We'll be submitting the commands in Spark on a driver, like what we have on our laptop. And then that would go out across the cluster. There'll be different worker nodes. So when you first start running this code, setting up the base RDD, determining where the endpoint is that you'll be loading data from, that's the first step, and then transforming the RDDs. That all happens, it's really more of a logical kind of statement of what needs to happen, creating a graph of your business logic. None of this gets executed. But we do have a notion of a graph that's built up. Spark knows about what needs to happen. And if you were to take a look, if you were running this code, and you were to take a look at that line value messages equals, et cetera, we can actually print out what the graph to be executed, what that looks like. And you kind of read this from the bottom up. The very bottom it says we're going to go out to the log files in HDFS. So we create an RDD, Hadoop RDD. And then from there, there's a filter, there's a couple of maps, the different transforms that get applied to it successively. So now going down to the first action, this is when the graph starts to get evaluated. This is when some type of computation actually starts happening. So to see that illustrated, let's say that we've got our log files out on HDFS, and those are out in the worker nodes. So we've got the data partitioned into different blocks out in HDFS, shown there, block 1, block 2, block 3. The driver will send out the code to be evaluated out to the workers. It's actually executors on the workers that are performing the work. They will read. And this is all happening in parallel out on the different worker nodes. The different partitions of data are being read in. And then some type of processing is happening. And the processing is the commands up above, that graph is being evaluated. Those functions are being applied. The results of that get cached. So the results, the RDD, is in memory. And then the counts that we need, all the partial counts, are put together and brought back down to the driver. So we'll see the results of this, the final results, back at the prompt. Now that's the first action. If we take a look at the second action, we've already got a lot of data in memory, in cache, so we don't need to hit the HDFS again. So it's a slightly different sequence there. Basically, we process it from cache, and then the results go back to the driver. So that's where you get more of a pipelining effect out of Spark. The notion is that you can leverage in memory much more and get rid of some of the synchronization barriers that you would typically have in MapReduce and get more of a pipelining effect. Again, because we had two actions that were using the same transformed RDDs. We'll go into this in much more detail, but just in terms of how does Spark work on a cluster, there's the driver and the worker nodes, and the executors out on the workers. This is the general sequence of things. Okay. Any questions about that? Yeah. Yeah, I mean, if for whatever reason those partitions were all evicted from memory, yes, it would go back and rerun it. We'll go into that. That's actually a lot of the basis of where the parallelism comes from, also where the fault tolerance comes from, is by that ability to rerun, if you will, per partition. Other questions? Yeah. Block size. Well, I'm probably not going to go into that too much, but anybody want to field in terms of configuration on block sizes? Let's go into a little bit. Well, maybe we'll cover that a little bit later on. But okay. Well, no. I mean, it's partitioned, right? So that'll depend on you've got the Hadoop input classes, right? You've got the kind of partitioning we typically have with HDFS. So in terms of how is it all chunked up, yeah, you can subclass those if you need to. Yeah, question right here. Exactly. Yeah. So the question there is. The worker nodes don't all have, do they have to be the same size configuration? Can they be a mix of heterogeneous resources? And it's the latter, yes. They can be a bunch of different kinds of resources put together in a cluster. So it may be that you've got a number of executors or partitions that are running there. Yep. Question? Yes, the cache. So yeah, what we're talking about is the memory cache in memory on the worker nodes. Good stuff. Other questions? Yeah. Well, or chunks of it. Yeah. So we'll talk more about this a little bit later on in terms of graceful degradation. If you have enough memory to cover the whole working set of what you'll be processing, great. If not, then it will manage spills out to local disk. And in the worst case, it's just spilling everything. It's just chunking through, which is kind of what you typically do with Hadoop anyway. Yeah, that's a great question. Yes? Well, it depends how you're writing your code, and you kind of do have to be careful about that. You don't want to go out and collect terabytes that come back to your driver, right? So, I mean, typically, if we're working with a large distributed data set, you'd probably write it back out to HDFS or S3 or Cassandra or some other kind of distributed store so that you weren't dumping everything back out to the driver. But your question was, if you're not in the REPL, if you're running an app, what's going to be the behavior? It'll be virtually the same behavior. So you just have to figure out where do you want to collect the data. Does that answer? Okay. Yeah. Yeah, I mean, the thing is, it's just there are two different counts. So they really will, yeah, there'll be different business logic in terms of the actions. Because they've got a different filter, and then you're taking account off of those. And the thing is that you've got, partial counts out on all the workers. You're basically aggregating that back. In this case, it's not a big deal because, you're just going to end up with a count for each action. But if I were doing, I could imagine other cases where I could get a whole bunch of data dumped back to my console, which typically I wouldn't want to do. Good stuff. Any other questions? Right here. Okay, how about here? Wow. Can you actually read this out there? I know this font's a little bit small on the screen. I want to show a slightly different view of this. The notion being that if we take that same sample code and let's say we've got a base RDD where we're pulling in the files from HDFS, we're creating an RDD. RDD is called lines. Then really another way to look at this is that we're applying a lot of transformations essentially different projections off that RDD. And then finally, we take some kind of action, and the action results in a value. So we see this pattern repeated over and over. It's a slightly different way. I wanted to show kind of a graphical way of looking at the flow of the code. Any questions about that?
So is each RDD still in memory as the next one is being generated, or is it flushed out, or how does it track?
So that's what's interesting about this with the RDDs is up until the action, nothing's happening. So there may be cases where actually the logic can be, you can get some function composition going on. So it may be the case that they don't need to have separate copies of each one in memory. You get this pipelining effect. And that's a... Well, you can force that. Yeah, you can force to cache the intermediates. We'll talk about that later because there's some great use cases for that, especially if there's branching off the results. You'd probably want to do that. It's kind of like an in-memory checkpoint. And it could also be partially in disk, too, or fully in disk. But the notion with the RDDs is that these transformations, there's lazy evaluation for them. And there may be opportunities essentially to optimize the query by composing them together. Yeah, question? Yeah, no, the graph is evaluated in terms of, where would a shuffle be required, or where is some action that's requiring some result to come back. So actually the whole graph is lazy. But the way it's handled is, this is being executed out on partitions. So for instance, a real benefit there is, because of the lazy evaluation, if one node dies, you can just grab the neighboring copy of that data and rerun the graph there. Or if it gets evicted on that node, then you can just rerun it. And so you get the fault tolerance, you get a lot more parallelism, you also get the pipelining. Yeah, questions?
So with those transformations, is Spark itself or interpreter smart enough to do intelligent things with transformations in terms of optimizing the software, or does the programmer have to?
No, that's actually a real benefit from the, so the question was, given these kind of transformations and building up a graph, to represent the program, it's a query graph. It's much like what SQL does when it builds up a query graph, and for much the same reason. So the question was, does the programmer have to be smart about how to compose these, or is Spark actually doing optimizations? Is that fair? Yeah. So no, it's the latter. The rhyme and reason of this is that then the query planner and the compiler get to do some smarts and be able to do some optimizations there. So it's very much an applicative system where you've got this function composition going on. You can leverage those kind of optimizations. Yeah. Yeah. What kind of caching? Uncaching. So as far as like, you mean could you force evictions? I don't actually have an answer on that. I haven't seen anything like that. Anybody, that's a question for Databricks. Can you force evictions? What? Unpersist, okay. Good stuff. Question there. Okay, let's bring that back up. So yeah, the line there, after we've done these transformations, there's a line in there that says messages.cache. And it doesn't have to be there. We've decided to put an explicit persistence there. So we say cache, and by default, that's going to put it into, cache it in memory. What it's saying is the value messages, the RDD, the transformed RDD messages, is something that I'm going to ostensibly reuse. So I want to try to see if it's possible to checkpoint it, if you will, in memory, so that I can reuse it multiple times. And here I've just got two different use cases for it, action 1 and action 2. But I'm telling Spark that I have a notion of essentially branching the graph there, and I'd like, if possible, to keep that around. It may be that I don't have enough memory on all the nodes to do that, but at least it will try. Yes, yes. Did you not hear the last one? Was it or? Okay, certainly. We'll try to be more careful about repeating questions then. Yes. Yeah.
So you run messages dot cache. When you run messages dot cache, any changes in like, the data set from messages won't reflect anything new after that?
Well, okay, that's a good point too. So these are values. These RDDs are immutable. Yeah. Okay. Sorry. Yeah. Thank you. Okay. This is a great question here. Is since there's a cache command there, so how does that affect if there's any changes in messages? So the data that's in the RDD messages, if there are updates to that, how would those propagate through the cache? And that's an excellent question. The RDDs, what we're describing here, these are immutable. So there won't be any updates to them. So once you define messages, it's a value. And so that's a nuance about Scala. If you see val, it means that that variable will not be updated. But the RDDs are immutable. So that means that, yeah, we can do some smart things with caching in that case. Yeah.
That's until the next action, right? Or the next point where something has actually an action applied to the data. So now the transformation will not be applied to the messages, but an action it will update again, right?
Right. So the question is, the transformations won't be applied until the next action.
At the next action, the messages will cache, the messages will be updated, right?
So the question is, will messages be updated? Messages will essentially be created, if you will. That transformation will be applied, and so that RDD is basically is like a materialized view, if you I guess would be another analogy. But once it's created, it's never updated. Yeah, so they're immutable data. Question?
In this conversation, are you talking about pending data or updated data?
The question was, in this conversation here, as far as about messages in this RDD, are we talking about appending data or updating? No, it's immutable. So it's what's there is there. Now there's other ways to handle that. We'll talk about it a little bit later. But for these here, once you've got the RDD, that transformation is a view of things. Other questions?
So, Scala inherently supports both mutable and immutable, but is there any mutable form of an RDD?
A mutable form of an RDD. I mean, part of the basic idea of an RDD is no, it's not. It's immutable. I don't know if anybody has any other examples of something that would be a mutable RDD. I can't really speak to that.
These are well, somewhat inherently short-running programs, right?
So, sorry, question?
I'm just saying these are inherently short-running programs,
Yeah.
so that's kind of the whole point.
Yeah.
You can make all these under assumptions because it's not.
Yeah, exactly. You're buying a lot by having that immutability, and you've got essentially what's a working set view of your data and how you're transforming your data. So you're buying a lot from that. That's part of the essence. Okay, I'll take a couple more questions and we'll move on, but these are great questions. Yeah.
The Anatile guy with distributed data frame, I think that they set that up so that can be immutable.
Oh, yeah, okay. That's interesting. Yeah, I caught that in the data science track yesterday when they were doing that. Yeah, so there's a question here, or a comment about Atatau and how their work with distributed data frames, a slightly different kind of paradigm. But we're not going to look at that kind of here, but that would be something to check out. One more question I saw over there.
So how would Spark deal with cases where messages didn't fit in memory?
Where messages didn't fit in memory? Essentially, you're going to get some chunking going on there. The idea is that there's graceful degradation on the RDDs. So if you can fit your working set into memory, you're fine. It'll use it. But if you can't fit it, then there'll be a graceful degradation in terms of spills out to local disk, which is sort of what you would be doing with Hadoop anyway, right? Doing the spills for chunking through data. Okay, one last question. What you got? Okay, the question was, can we get the amount of memory that's available? And then be able to configure it differently?
Well, so that I don't know that my state so that it will
Interesting. Well, I mean, from the UI, you can get some stats. If you want to see how things are operating, you can see in the different stages what the resources are being used. So you can get some metrics back on that if you wanted to change configuration. But I think, is your question more about programmatically, would you want to be able to control that? Well, I'm not going to go into that detail, not for here. We can talk offline more about that, but good stuff. Okay, let me move on a little bit here. Okay, I want to shift gears a little bit and show some apps. Here is a word count. And I'm sure, has everybody here seen word counts before? I'll kind of take as a given. Word count is kind of a hello world for big data. It's really a canary in a coal mine. The thing that's interesting about word count, why we use this over and over, is that it's a very short, concise program, very simple program to write, but it includes parts that are both numeric and parts that are symbolic. It has parts that can be parallelized, other parts that are very hard to parallelize. So if you can do word count efficiently at scale in parallel on some kind of framework, then you've got a good idea that there's a much broader class of interesting problems that can be solved in parallel and scale on that kind of framework. So it's a kind of canary in a coal mine to prove out the distributed frameworks. And over on the right-hand side, the code there, that's some pseudocode for being able to run word count, typically on MapReduce, on Hadoop. And the idea is that you take a whole bunch of lines of text from a collection of documents, and in parallel, you cut those up, segment them into words, keywords, and then for each keyword, you emit a tuple that's the keyword and the number 1, the integer value 1. And so your mapper is just slamming through all your text collection of documents and emitting keyword and value 1. The reducer gets a shuffle of this such that for each keyword, you've got all those 1's values, and they're all collected on the same node. So your reducer sees that. It gets the keyword, it gets all the 1's, it adds the 1's together, and then emits the keyword and the sum, which is the count, the word count. So it's very straightforward, and that's a good way to parallelize the problem. Both the mapper and the reducer, map task and reduce task, are running fully in parallel then. And word count's interesting because it's just a few steps away from being able to do some interesting work, like a TF-IDF, the kind of algorithm that's sort of at the heart of, say, Lucene for being able to do text indexing. So if we want to try a word count in Spark, I'll do the Scala and then the Python. In Scala, it's just a few lines of code here, and then we'll show an example of saving it out as a text file. I'll be working with the README, the local README in Spark. I'll use that as input. So we'll say here, try this, cut and paste this. Inside of the Scala prompt, we've got value f equals sc.textfile README. So from the sc, from the Spark context, we're going to read in this text file, readme.md, and we're going to create an RDD out of it. The RDD is called f. So is that working okay? Right. Question? Oh, gotcha. In this case, it should be, but you're right, you're right. So the question was, should we have absolute path on this? And I'm making the assumption in this code that the README file is in the same directory as where we're operating out of. Just for these examples, that's valid, but in general, you'd probably want to have more management of the path. Good point. Other questions? Okay. Okay, so we've got an RDD. It's called F. Let's cut and paste the next line. Try that out. There's a bit more logic here. So we'll say value WC equals f.flatMap. So the first function there is we're going to take the F, RDD, and apply a function flatMap, and then from there apply a map function to get the word 1, keyword 1 tuples. And then from there we're going to call another function called reduce by key to sum the 1 values together. And that'll produce the word counts. So this is interesting. There's a function here called flatMap. It's different than a map. And the notion is that we've got this big collection of text. Assume that we've got a whole bunch of text files. And we're going to be looking at those. The text file function reads them into an RDD where each element is a line out of text. So they're split on the line breaks. And that'll be coming into our flat map. And what flat map does is you can think of this data or the results of processing this data as being a list of lists. Each partition is going to generate some list of keywords. What we'd really like, though, is to have a much flatter kind of space where we've just got this big collection of keywords. Because downstream from here, after we've cut the text up into keywords, we're going to apply some logic on the individual keywords. So instead of using a map, we use a flat map here, such that the results are to this one big space of keywords. If we hadn't done that, then we would end up with basically a list of lists, and we'd have to drill down further into it to be able to do the processing. So you see flat map used a lot in terms of initially getting your data there, flattening out this space. But the long and the short of that is we apply a flat map and we say L goes to L dot split and then a space. So what that says is that for each element that's coming through, there's a line, and we're going to split that line on the blanks. And so a very simple case of creating keywords by segmenting on the blanks. Question?
Can I save the new state so that I can make a new HDD or a new RDD and continue to accumulate the word count?
So the question was, can you save the intermediate state so that you could create it to do?
Reduce state. So reapply the map state on a new RDD and accumulate the
And be able to accumulate. So you could have branches here. I've done, what, 1, 2, 3 different function calls off the same RDD before I actually create another RDD. There's actually transforms all the way in there. I could have carved this up into, each step would have been its own value, and then I could do other things with it. Generally, when I'm writing Spark code, actually that's how I write. I don't put it all in one long line. I wanted to make this simple to cut and paste the lines. But generally I personally write a different value for each different transformation, especially if it's something complex, because it's easier to debug that way. Then I can go in and just execute to a certain point and take a sample out of it. That's just one kind of debugging technique that I use. So yes, very definitely you can. Other questions about that? Okay. So if I execute this line, it'll segment the text into keywords and then emit the keyword 1 tuple, and then it'll count up all the results. And we'll do other examples to break this down even further, but I want to show an app. So when I run this, it comes back and it says, okay, you've got an RDD. The results in the RDD are going to be tuples of string, keyword, and int, count. Nothing's happened yet, though. We've just defined logically what's supposed to happen. We've defined the graph of what's supposed to be evaluated later on. So now we'll take an action. The last part of this is to say WC save as. So we go back to this value, WC, this RDD, and we call the function save as text file and give it a path. Again, I'm assuming I'm just working in this directory. In practice, you'd probably want to have more management of your path there. Actually, in practice, it would probably be going out to something like HDFS or S3 or Cassandra or some other kind of distributed store. But in the simple case here, we'll just save the results off as a text file. So when you execute this, this is an action, and this is where the lazy evaluation comes in again. The graph is executed. Great. Now, ostensibly things happened. So let's take a look at that. I'm in a different window here. If you bring up a different terminal window, you should be able to take a look at this. But there's a file that's created, wc_out, and underneath that, this is a partition file. So you've got partition 0, partition 1. I'll take a look at one of these here. Okay, great. So now in this partition file, then, I've got all the results from the word count. You can see at the very top, the word 4 shows up 5 times. Later on, Cloudera shows up 4 times. Library shows up once. It's a real simple word count. In practice, I'd probably do a lot more processing to clean up the keywords. But we got some results. Is that working out for everybody? Or is it, anybody having, are there any issues on Spark at this point? Okay, question. Pardon? Right. Again, that'll be the configuration, and you may see more than, so the question was about the partitions. For instance, here, the results of what I had saved out under WC out, you see that there's 2 partitions. And again, that comes back to what kind of resources are available and what kind of configuration you have. Some laptops, you may see 4 of these, or there'll be differences across different environments. For my laptop, I've got 2 that will come out. Any other questions about this? Okay, so that's a word count. Word count in 3 lines. Yes?
Does the API state what's lazy and what's not, or is that something that you learn over time?
No, it's very explicit. So the lazy evaluation is for transforms, and then the actions are when things start to happen. So we'll go into that in a bit, but the API is really broken out into what's the transformations versus the actions. Yep, great point. So that's very explicit. Another question back there. Sorry, could you repeat? Gotcha. Okay, so the question was about the file size and the output, if that could be compacted into, say, 1 file. You know, so this is something you'll see across with Hadoop in general, with HDFS in general, where you're writing partition files. So you get the output as partition file, and it may be the use case wants to have this all together collected into 1 file for a result set. So you could do some post-processing on that. There are ways to force it into 1 file, yes. A little bit more than what we'll get into here, but yeah, there's ways to do that. Other questions? I saw some other hands up. Okay, good stuff. Let's take a look here. Okay, so in 3 lines of code, we have a word count, and that comes in pretty handy. You know, there's a lot of cases for slicing and dicing log files and doing text analytics, and they usually start out with something like this. If I wanted to do this in Python instead of in Scala, it's pretty much the same thing. Let me bring up a Python prompt. So back to here. Okay, I've got my Scala prompt. I'm going to quit out of that. I just do a Control D and I'll stop that. There we go. So to get into Python, it's /bin and then PySpark. Again, if you're on Windows, you're running in a DOS shell, it'll be the .command. In this case, though, I'm just running PySpark on my Mac. So try that out, get into Python. It does require that you have Python 2.7. If you need to download that, we can help you out with Anaconda. We can put that on a USB stick, or we can download it from the directory, or sorry, from their Continuum's website. But just to illustrate, when you get into PySpark, it's a REPL. It's not your Python environment. If you're familiar with working with Python, it's not Python directly. It is a REPL, but you can evaluate Python code. So I don't know, I could say X, 1, 2, 3, 4, something like that. I could create a list. I can do Python things there. Now what I want to do is back here. Number 1, Python needs an import for the add operator if I want to do the example below. So I'll just do a simple import. And then very similarly, bring in, create an RDD. In this case, the syntax is a little bit different than Scala, but I say f equals sc.textfile readme. And so the same thing here. We're working from sc, the Spark context, and we call the text file function to load in some path, in this case the README, and that creates a variable also an immutable variable, the results are immutable, they're an RDD. Take a look at that. Now, the next line would be a similar kind of business logic for word count done in Python instead of Scala. So taking a look at this, we've got WC equals F through the RDD. We call flat map. Inside of the closure there, inside of flat map, now instead of an anonymous function like we would have in Scala, like we did before, in Python we'll be using lambdas. And Java 8 has lambda expressions now too. It's fairly similar. But the idea is we say lambda x, so each element of the RDD is going to be a line of text, and so that's the variable x in this lambda expression. And we say split that string, split it on spaces, so we're doing segmenting the text to get the keywords out. And then similar to what we had before in the Scala, we say map, and for each element we turn it into a tuple, keyword, and then the number 1. And then we say reduce by key, and we apply the add operator. So each key is going to be the keyword, and then all its values are going to be the number 1. We apply this operator add to sum those together to get our word counts. So you got a little monoid add going on there. We'll talk about that in more detail later. But when you run this, nothing happens yet. It's just define the graph. And then down here, pretty much the same thing. wc.save as text file. And just to be sure, I'm going to go back in here and remove my wc out text. That's important. Hadoop has problems about overwriting files, so I'm going to make sure that I don't try to rewrite the file. All right, but I say wc.save as text file, wc-out.text, and it'll write it. And again, we'll come back here, and we have a part file created again. Actually, so if you look inside of the part file, in this case with Python, it created 4 different part files. If we take a look at one of those, it'll be wc out part 1. And I mean, the syntax of output from Python will be a bit different. You've got these strings, UTF strings, but essentially you've got keyword and value. Okay. Yeah. To get to a CSV format. Yeah, later on. I mean, I've written apps like that where, yeah, I get down to having some kind of result set, and these part files are tab separated by default. And I may do some sort of post-processing. Like, I was working for a client doing a financial app where they wanted to do a lot of technical analysis on stock trades, but then they wanted it in spreadsheets. So, we dropped it down we did our results, we did our time series analysis in Spark, and then we got the end results, and we converted those to CSV just by using Python's, there's a good package for that. I'll have to look up what the package is. I've got the code I can build up here, but that's an interesting point to illustrate. If you're working in Python, there's a whole bunch of different libraries that you can reuse. And so for instance, I had one case where they wanted spreadsheets. So there's a nice spreadsheet package. You just import that. I got the results out of Apache Spark, and in the same code, I just at the end of it generated an Excel spreadsheet. So you can mix and match the libraries, no problem. Yep.
Doesn't the difference in the output format reduce the compatibility between languages?
Yeah, that's a good point. So the question was, does the difference in the output format reduce compatibility between the two formats? Because you saw Scala is just going to drop you out a string. The tuples look different, right? You've got the string and the count, whereas with Python, by default, it's going to print out strings as that UTF format that they've got. Yeah, that's a good point. It does kind of reduce the compatibility of being able to mix and match if you're working with strings. UTF and string encoding is kind of always a problem to have to deal with at that point. Sorry, the R. So for consistency, is the R output? You know, I haven't really worked a lot on strings with Spark R yet. I'd have to check that out. But I can imagine that when you get into different types of string formats and encodings, there's going to be some differences. Good point. Without more serialization, using something like Avro or whatever, some kind of serialization format, yeah, that'll be a problem. As you get into more serialization methods, hopefully that becomes much more consistent. So if I was doing a serialization method coming out of PySpark, I could expect that I could run those results through Scala or something and not have that problem. Other questions? Okay. Let's see here. I think the next slide is how many do we get? So let's check that out. Let's see what the results look like. Grab here. I'm going to do a grep for keyword Spark out of all these part files. Okay, and there you can see, you know, this is a real cheap and dirty kind of segmentation, so it didn't clear out a lot of garbage on the end of the keywords. So if I look at this, the first one says Spark, but it actually has a period at the end of Spark. There's 2 instances of that. But if I'm just taking it at face value, the number of instances of just the word Spark was 12. Hopefully that's the same. Hopefully everybody's getting that answer. Or if anybody isn't getting that answer, let me know. All right, did that work out okay? Good. Okay, so the next is a little bit more, well, I'll just show kind of a conceptual view of this. I wanted to show how to do a join, because when you're working with big data, usually, you know, the first thing is you start bringing in data from some kind of endpoints, like HDFS or S3, and then probably the first thing you're going to want to do is some kind of join. Cleaning up the data preparation, going into machine learning training cases, things like that. So I wanted to show an example of a join, but also at a conceptual level, show what's going on under the hood in Spark when a join happens. And that gets into developing the notion of different stages of processing, looking at the parallelism, looking at the caching, etc. But first off, let's see about the join. And if you want to follow along on this one here, or cut and paste, I've got some simple files that I don't think we made these onto the USB sticks. Let me check. We do. Great. Okay, so in the USB sticks, the data that you copied over from the USB sticks, there should be a directory called data. And so if you look at /data, there'll be another subdirectory called join. And then under that, there'll be 2 files. One of them is reg.tsv, and the other is clk.tsv. And so these are real short files. You just want to copy them over. I'll say copy reg here, and then copy clk here. And it's just going to be a couple of records on there, but if you look at clk, it's a tab-separated file. This is supposed to represent some clickstream data. So I've got 2 different files that I want to join. One of them is supposed to be basically users clicking on a website. So you've got a timestamp and then a UID and, I don't know, maybe some kind of landing page identifier. But real simple records, and there's 2 of them. And then if you take a look at the next file, let's see here, reg. Reg.tsv is where, after people have clicked, then some of them will start to register on the website. So the format there is you've got a timestamp, you've got user ID, some other metrics that we're collecting, lat long, things like that. But the point is we're going to want to join these files together. So if you've got those copied, then next step is I've got an app here that we want to work with. This is in Scala. It's actually using a Java library. The first line there is to use Java text simple date format. So we're going to take and parse that timestamp, that date string, and we've got a formatter for that. So let me bring this in. Okay. I'm going to call bin Spark shell again. Load that up. Make sure I don't have it running anywhere else. Good. Okay, so I've got bin Spark shell. Once you're at the Scala prompt, then come back over here to slides. We'll cut and paste this first line and create a date formatter. Okay, great. It's got a Java date formatter that's instantiated here. Now the next thing is I'm going to copy this next line here, a case class. So this says case class. It's defining an object, a class. We'll instantiate objects for that for each line out of the register file. But I've got case class register, and then I've defined all my different columns in the data. I've got the timestamp, I've got the user ID, customer ID, and then latitude, longitude. Great, so we've created a class definition to be able to use. We'll use this in the join. I'm going to do another one of these for the clicks. So cut and paste this line. Case class, click. And again, it's got the timestamp, it's got the UID, and then another field. It's got a landing page field. Okay, so we've got those two classes defined. We'll pull in some data next. Cut and paste these next 3 lines of code. Try this here. So this says I'm going to pull in the registrations data. So I've got a value reg. It's going to be an RDD. And first off, I call sc, Spark context, .text file, and load in the local file, reg.tsv. From there, I'm going to map. And so I'm saying for each element, for each row in that TSV file, I'm going to split it on tabs. The \t is basically saying it's tab-separated data, so we'll split on tabs. At that point, you've got a tuple. For each element, each row, you've got a tuple. And the line here where it says R goes to parentheses R1, comma, register, et cetera, what we're doing is we're operating on that tuple. So we're saying we've got a tuple of 1, 2, 3, 4, 5 values. We're going to pick out one of those. It's actually the second value. This is zeros based, so we're saying R1. And that's the UID for the user. We're going to designate that as the key. And then the rest of it is going to be this class register, this case class that we're instantiating, has all the rest of the values there. So what we're doing is creating a tuple that's key value, KB, and we'll use that for the join. So we're reshaping the data, if you will, into a key value structure. We're designating what the key is, and then we're creating this object based on the case class. And you also see inside of register there, we're calling format.parse on R0. So that's going to take the date string and then format it into a timestamp. A little bit later on, you see one of the fields, actually 2 of the fields, the lat and the long, those are converted into floats. So this is just a flavor of typical kinds of ETL that you would do, reading in a TSV file, and then converting it into a key value format. Okay, so if I run that, it creates an RDD. Nothing's really been executed yet, but that part of the graph is defined. And now the next step, we'll cut and paste the next 3 lines. We'll do a similar thing to the clicks. So we're saying an RDD, CLK click. We're reading it in from the TSV file. We're going to map and split each line on tabs. So now we've got a tuple. And then inside of another map, we're going to say that that tuple, we're going to pick out C1. Again, it's 0 indexed. So the second column is the UID. That's going to be our key. And then the value is going to be this click object. So we're creating another key value pair out of this. I wish I had a whiteboard, actually. I'd show what the key value pairs look like. But again, we're calling the formatter for the timestamp. And you can see at the end it says, take the strings, trim them, convert them to int. Typical kinds of ETL things that you'll do as we're processing these files. Okay, great. So that creates another RDD. Is that working okay? Or any questions about this so far? Okay. Now, to do a join is quite straightforward. Let me clear my screen here a little bit. To do a join at this point, I've got two RDDs. Both of them are structured as key value pairs. So to do a join, I would simply say reg, one of the RDDs, dot join, called the join function, on the other RDD, and it will, Spark will execute a join based off of those keys and collect the values together. And let's just, let's take a look at just one of the results. So I'll say take one, and that'll show the first result that comes out of that join. Great. So it comes back and it says, I've got an array, my result set, and it's structured such that there's a string, my key, the UID, and then the values that are joined together, it's the register class and the case class. I've got those together. So you can see from the first element of this, I've got a UUID, and then I've got a registration and a click. Now, in practice, I'd probably want to do things with these fields, combine them together in some way. But the point is the data is being organized in a join. And to do that, you need to get to that shaping, that reshaping with a key value. If I do the full thing, I could also say collect if I want to show all of it. Great. And I mean, there's only 2 records in this file, so there's not a lot going on, but question right there.
Yeah, so is that doing the inner join or outer join, and how would I do the other one?
Yeah, there's different flavors of it. This is doing, by default, this is doing an inner join. We'll show more about that. You can parameterize that. Question?
And we have one of the sources from MySQL.
Sorry.
And we have one of the data sources from a database.
Ah, interesting. Okay, so the question was, could we have one of the sources coming from a database, such as MySQL? So the RDDs could be coming from a variety of different sources, yes. You could be getting data out of, say, HBase, or Cassandra, or S3, or wherever some type of input format is defined. There's support also for pulling in from JDBC, so yes, it could be coming out of a database. Yes?
What if I wanted a composite key?
A composite key. You can structure those. I mean, we can structure the key values for that.
So instead of scalar, I would make it a list?
Exactly, a tuple. Yeah, that'd be a way. Good point. Yeah. Can you have secondary keys on this? I'm not going to go. We can talk more about offline about more complex joins. I just kind of want to do a simple one here. But in terms of this function here, the simple example, the default example, is just a key value structure. So just primary key. Other questions? All right. Let's try something here. This is really useful for troubleshooting, but also to understand the logic of what's happening. Again, it goes back to the fact that we're creating this graph, and there's going to be lazy evaluation on the graph. So sometimes it really comes in handy to see what is the graph? How is it actually defined? So for instance here, I've got an expression, reg join click, and then I can call this other function toDebugString, and that'll reflect back what the graph looks like. So you can do this at any point, and you can do this on any expression of RDDs, and nothing's getting evaluated here. This is just really showing the business logic of what will happen when it's evaluated. But you can see this is essentially well, it's a graph, but you can see kind of a tree structure here, starting from the bottom. One of the files is pulled in, text file, and then there's the map and map. And then another file, slightly above that, is the text file pulled in, and then the map and map. And then the join happens. So this is interesting because it implies that the 2 bottom parts could be run in parallel. And that's typically what's going to happen. We start to see some parallelism come out there. Another way to look at it would be to say this graph could be executed in stages. So stage 1, loading in one of the files and doing those maps, doing some ETL, reshaping it into key values. That's stage 1. Stage 2 is with the other files, same thing, that kind of transform. So this ETL and the different files could be done in parallel. But then you reach the point where you need to do a join between them, and that's stage 3. And that's going to require both stage 1 and stage 1 to have completed beforehand. So by doing the lazy evaluation, then, you can get some level of parallelism in the sense of just breaking it into stages that can run. All right. The other thing is, now this is more conceptual. It's not necessarily what happened when I ran that. But I was just trying to show the idea that depending on what your cluster looks like, you're going to have these functions operating on different partitions of data. And some of those may be cached. Some of them may not be. But you want to think about that when you consider the logic of what's happening in the graph here when it's being evaluated, that there could be elements that are already cached. And what kind of impact is that going to have on how your program operates? All right, any questions about that? You're right there.
Yeah, so if we knew that these were already sorted, then we could do a more efficient and lazy join on this. Is there any way of telling the join operation that these things are sorted and presumably already chunked by the key and this can all happen?
Ah, gotcha. So the question is, could you do a more sophisticated kind of join if you knew that these elements were already sorted? There are ways to actually force a sort in the whole business logic of the graph there. So yeah, you can start to put that in if you need to. And you can also get iterators and work on stuff in much more detail. You can work with code groups and get the iterators for them, etc. So yeah, question? To see, yeah, that's great. Oh, what's in cache and what's not? Excellent question. So the question was, is there something analogous to a query plan so that we can see what's going to be executed and what's in cache and what's not? The graph that gets printed here in terms of 2 debug string is not going to show you anything about the caching. It's much more at a logical level of, again, the lazy evaluation. So effectively, that is your query plan. And it's interesting, too, because we'll look at Spark SQL later on, but if you look side by side of using the functional programming to accomplish a join versus using Spark SQL to accomplish a join, you see in the latter a very explicit query plan, but it's pretty much the same thing. And now as far as drilling down to find out what's cached and what's not, you can get some of that information out of the UI, but not at this level. Question?
Is there something we should make a point of understanding about these different versions of an RDD? What's behind the Hadoop RDD?
Yeah, good point. So the question is, there's these different versions of the RDDs, and what's the takeaway from that? What do we derive from seeing those transformations? And the point there, or if does that capture? Okay. So the point there is, yes, there's the base RDDs, the Hadoop RDD. Those are the base RDDs where we're pulling in data and initially creating the RDD. It's a Hadoop RDD. We're basically wrapping some data that's down in HDFS. Now, everything else from there is a transformation. So as you're reading this, one of the takeaways is you've got Hadoop RDD as your base RDD, and then you've got these 3 maps on top of it. In terms of lazy evaluation, those can be composed together, most likely. That's one thing that you could read out of this. Once you get up to the code groups, when you get into the code group, something's going to happen there. That's the join is based on the code group. Question? Yeah. Does the cache understand about the size of memory on different nodes?
Each node has a cache of one of the smaller bytes in memory.
Okay, so let me see if I've got, if I'm understanding, is there, like if you had asymmetric, if you had a right-hand side that's much smaller than the left-hand side, could you cache data? Okay. So if I understand, question is about, when you're doing a join, does Spark understand about the size of the data and be able to do something interesting in terms of, I don't know, maybe like a in-memory join, hash join kind of thing? So, that's great with big data. Certainly in MapReduce, I've done that a lot before, where you do a hash join. If you're doing a query on a large amount of data and it's asymmetric, so one side of the data, say the left-hand side, is a very large file, and it's being joined with, I don't know, maybe some metadata or like a stop word list or something that's relatively small. So the right-hand side might be much smaller. There are ways to do, like I say, in MapReduce, you can do hash joins, for instance, where you just replicate the right-hand side along. And there are flavors of that here, yes. You can get to more expressive kinds of joins through the API. Now, does Spark know about that directly? If I'm working at this level, no. However, if I'm working inside of Spark SQL, then there's other kinds of optimizations. Catalyst is an optimizer there. And there's a lot of smarts built into that. I don't think we'll go into that level of detail in the course here, but we can grab some of the people who, if you want to talk offline about Catalyst. Other questions? Yeah. Pardon? The numbers? The numbers in this output here. So it's saying console 16 and then console 23. Effectively, those are like line numbers. So since I'm typing this in at the REPL, it's got some track of where I am. It's mapping my console line to my line number. Exactly, yeah. It's tracing back. The graph then is traced back to the source code. So, ostensibly you could do something pretty smart with that. I don't know, maybe that'll emerge down the line here. But the idea is you've got a very nice correspondence between your actual code and what the graph is for troubleshooting and tracking metrics, things like that. What?
Numbers actually can refer back when you generate a command, the response to that command has the number in it, so you can actually refer to that. So just making a comment. If you look at the console, the numbers is printed out when you enter.
Yes. Yeah, that's a good point. Yeah, so if you go back to the console log, then that's being, it'll probably have different things here, but unfortunately I'd cleared off, I did a Control K, but the numbers are back there on the console as you're executing these commands, so you could refer back to that. Good point. Other questions? Okay. Let's try an exercise, and then we'll take a break after that. And let me check what the time is. Okay, great. We're actually doing really good on time. Okay, so we took a look at how to do a word count based off of README. And we also took a look at how to do a join based off of like a key value structure. And a nice thing is that word count is essentially providing that key value structure. So you could compose those two kinds of business logic into one application. Let's try this out as an exercise. Create two RDDs, and one will be from the README file, and the other from changes.txt file. Wow, let me verify one thing. Let's see what we've got on this. Yeah, good, okay. Just making sure. So we've got readme.md, and we've got changes.txt. Those should both be there in the local directory. So for the assignment, create a word count out of both of those files and then join it together so that we can see, what the combined tuples look like. And I think the question on that is how many Scala keywords show up in the different files respectively. So let's try this out as an exercise, writing at the REPL the program that you need to do to load in these files, do the word count on each side, but then join the results together. Oh, for the results, well, we'll get all the output out, and then we can just grep inside there and take a look for Scala. Yeah, that's a great point. Sorry, I skipped over that. My mea culpa. Yeah, we'll create RDDs, and we'll filter out for the keyword Spark. We'll run word counts on those, and then we'll join. So you're right, there's actually 3 steps to this that pulls together all 3 of the apps that we'd seen previously. Good point. Question?
Join in Python?
Now, that's it. If you want to do this in Python, do you want to see what an example join looks like? Or, same. It's the same. Get the RDDs and do a join. So if you want to do this in Scala or Python either, this should work fine. Any other questions? Okay, let's try that out. And this is meant to be an interactive exercise too, so if you have any questions, raise your hand. Come around. Okay. A couple things to clarify. One is it says filter each file. You know, it's probably better to say each line, because the RDDs are going to be looking at line by line in each file. So I'll make that change. And then, let's see, the other change is actually if you do go to the next slide, it says how many Scala keywords are there. It should say Spark. Yeah. We'll call that. The main thing is be able to do the joins. So any troubles with coming up with the code for the joins so far? Anything we can help on? Question? We're at 11. Let's we'll give this like another 5 minutes and then kind of compare notes and move along a bit. But actually, after this part, we're going to take a break anyway. So, are there any questions? Yeah. At this point, definitely let's take a break for like 10 minutes or so. We had that built into the course. If you're working on this right now and you want some help on troubleshooting code, getting that going, we'll stick around and we'll help out. But if anybody needs to refresh your coffee or anything else, let's adjourn for about 10 minutes. Sound good? Hi. Yeah, I know. We'll probably do lunch. It sounds like 12 is when lunch comes, yeah. I'm just going to do a short segment just to get everybody back in. I should have probably done the break before, but we started at 9. We usually start at 8. Exactly. Yes. Yes.
Question about
Yeah.
the alignment of the direction. So, when you do flat maps, it's in this picture, right? You, so you find all lines, you fill lines, right? So it's a collection of lines. When you get those, right?
Yikes. Sorry. There's an open lead here somewhere. Actually, the way I did it was to do a flat map first, converting the keywords, and then filter it.
Why don't you grab it first? Why do you use this?
Well, let's think about that.
And that was my question. What happens first?
So,
Right? Because I would do it grab first. Like,
I'm trying to think, okay, so what's going to be better? It's more pure logic if you do split and then grab, because the notion is that you're still filtering at the line level otherwise, and then you're getting other keywords out. So downstream from the split, you won't have just the Spark, you'll have other things as well. We're going to close up here in 2 minutes. Yeah, the question is right. I think it's probably the way I would do it.
So now we have a collection of lines. So the way I do it, I have a collection of lines, right? And that's my line. So now I do a flat map, and then split. Well, there's a flat map split, right? So my question is this: does it mean that we first merge all the lines into one? What is flat map?
Flat map is basically saying that I've got this collection of elements. I'm going to produce other elements out of it. The transformation is split. What I don't want to do is have a many one map, or one many map. So I don't want to say for each line I've got this sublist.
I get it. What happens first? Do we merge sublists, or do we merge lines of those?
You do the last. I don't know if you do the form. So we merge the sublist.
So we split and then
Okay, let's see here. I mentioned we're collecting everybody back into the RDD, which is our class. And we'll get going here in a little bit. Let me try to boost the font size here. Okay, so this is the way that I would solve this. And I saw a lot of great approaches. But let's see. Do an RDD for README, and do the word count for README. And then let's see here. I'll do the same thing off of changes. Word count for changes. And then join those two together. README join changelog. Oops, sorry. Wow, I messed that up, didn't I? WC, join WC. There. So let me put this back into the code here. WC and WC. I can go through this step by step. And actually, is that readable? Yeah, that looks pretty readable. Okay, so the first line there, what I did was to create an RDD. I call it RM for README. So it reads in the README file, creates an RDD, and then the next line is where I create a word count, flat map, and then split, filter, and then map to my word tuples and sum them up. Probably if I scoot this over a little bit, it's a bit more readable. Okay. Now, for the changelog, same thing. I created an RDD called CL, and then I do a word count on that and get those values out. Then at the last part, I take those two RDDs for the word counts, I join them together, and I show what the results look like at the end. Back over here, let me try this again. Back over here, the end results come out to an RDD that has, so we've got this tuple key value. The key is the string, the word. And then you've got this other tuple for the values. You've got the count from the left-hand side and the right-hand side, respectively, readme and changelog. And it should come out with the results something like 12 and 101. So, sorry?
So, Joy, if you look at the intermediate results, there are a little bit different keys that contain Spark, something. With the join, config discards, it only joins keys that are completely exactly the same. And that's why we only get one key.
Yep. Yeah, so that's a great question. So if you actually look at the intermediate values, the way that, if you're using _contains Spark, then you'll get some keywords that have Spark inside of it, but at the end of it, when the join happens, you're going to join the values that just have Spark, that exact string, as the key. And it depends. You could do contains, you could do equals equals. The way that I had the logic defined, I think I used equals equals. Yeah, I did. So I did _ equals equals Spark. So I was filtering out everything else way up in the pipeline. I could have done a contains there instead, in which case I get other keywords that contain Spark that didn't equal it. But at the end of the day, by the time you do the join, you'll come back hopefully with this tuple there that's just Spark and has a 12 on one side and a 101 on the other.
Does that do it because we defined Spark as a keyword, or only because both files, the only thing that both files contain is Spark?
Well, I mean, if you segment it this way, yes, that's all the keywords that contain Spark. So, yeah, so one of the troubles is this logic could be expressed in several different ways. You could do it in different orders. Hopefully, you'll get the same numeric results at the end, but if you look at the intermediate values, they will be different in between. The question is how much processing is happening in the intermediate. Quick question.
Yeah, that's a design question.
Yeah, yeah. It's. I mean, it. Yeah, and it depends.
Set parameters that you want to do, not want to filter out exact Spark.
Yeah, that's a great point. This is really a design question of how you want to build your app, what your business logic is going to be. It might be that you need to parameterize this and not just go after one keyword, Spark, but do other things. You may have other reuses for the intermediate values, so you could restructure this in different ways. But you know, the main thing here is we just want to get through taking some earlier code, some earlier programs, and composing them together into a more complicated workflow that involved a join, because that's typically what you do with big data. You see this exercise of coming up with filters and joins over and over. Question?
So, right, so what really, is knowing really more than just join the two maps that kind of came out of it. So by default, anything that's a map structure, joins works on. He just says the key is good enough.
Yeah, exactly. So the question was that, you know, really we just had a couple of maps coming out of this, out of the filter, out of the word counts. We had a couple of maps, and they're organized in key value pairs, and anything that comes out in that format, you could join. Yeah. So it's very nice because you could get these from different types of operations, but then join just by having that simple key. Question? Great question. So the question was, what parts of this are Spark and what parts of this is Scala? And actually, the way that this program works, almost all of this is Spark. There's really not a lot of Scala going on other than what's inside of the closures. So for instance, here we do sc.textfile, that's Spark API. Flat map is Spark. Inside of the flat map, the closure in there, where we say L goes to L split, that's a Scala expression. And the same thing inside the filter, the closure inside the filter, where we say _ = Spark. Again, that's a Scalaism. If you were doing it in Python or Java, there'd be something different inside the closure. Yeah, the lambda would be different. The anonymous function here, yeah. But the function calls here are all Spark. I guess other than split. Good stuff. Any other questions on that? A number of folks asked about what time lunch would be. From what I understand, lunch is at 12. And that's important because some of us have to check out before 1. So definitely we'll take a long break well before 1 o'clock. If you need to check out, we'll be sensitive about that. All right. Let's go into a lecture here. Yeah, I can scoot through that. I want to shift over into doing a bit of a lecture about where this came from and what the motivations for Spark are, more from, say, a theoretical side, conceptual side. And I'd like to illustrate that in terms of starting with a timeline. If you look at the original papers about Google, the original MapReduce paper from Google, Jeff Dean and all, you know, that work on MapReduce is being done in about 2002. And it was published for a conference in 2004. And subsequently that got picked up. Doug Cutting and others were working on the Nudge project as an open source web crawler. And out of the Nudge project, Lucene is one of the projects that came out. They were building text indexes, and they wanted to use MapReduce to build the text indexes. So that's where the Hadoop project got started. That was adopted, well, that work was like 2005, going into 2006. And then later it got adopted by Yahoo. By the time that 2008 rolled around, we were starting, I think that was the first or second, but it was the first Hadoop summit where there were a lot of other parties involved, other sponsors. Now, along this timeline, Spark comes in, really it dates back to, Matei can correct me, but I believe there was a skiing trip over one of the breaks in 2009. Spark dates back to 2009, but one of the first papers there was in 2010. And then rolling the clock up to 2014, Spark went through the Apache incubator process, became top level at Apache in earlier this year, and subsequently made like record progress in reaching the 1.0 release status. It was a very, very quick process. What I want to illustrate here, though, is that MapReduce, again, dates back more than a decade ago, back to 2002. So our notions of Hadoop were really leveraging what kind of resources were available back then in terms of taking advantage of clusters of commodity hardware to be able to do fault-tolerant batch jobs. And a lot of the rhyme and reason of MapReduce was exactly that. Leverage functional programming, but take into account the fact that you're running on top of spinny disks and they fail at a certain rate. You want to try to maximize throughput for batch jobs. So, MapReduce was this fault-tolerant framework that would allow a large-scale job to run with guarantees that it would complete and still be able to get away with using commodity hardware. What was commodity at the time? There's a great anecdote about this. If you ever read some of the, if you ever watch some of the videos about the early days of MapReduce at Google, Jeff Dean had one from, I think it was like 2011 Google I/O, where he talks about they had deployed MapReduce, they had deployed an app in production, and they were watching one day, and the app was running like 30% slower. Has anybody seen this video? I can try to dig up a link, but it's hilarious because they noticed that this MapReduce, this huge MapReduce job was running, but it was slower. And they called down to the data center, and they found out that actually the racks were being replaced. So the ops team was going in and powering down a rack at a time, swapping in new hardware, powering it back up. And MapReduce still marched right along, and the app completed just a lot slower. But it sort of points to the fact that it was built for fault tolerance. And it really worked in that case. So hopefully you don't have to swap out your data center while you're running your jobs. Now, the point I want to make here is that Spark is coming about a decade later. And the reality of what we have in data centers is much different now. There are different kinds of issues, different kinds of things to take advantage of. But it's still this notion of applying really functional programming to how do we get the best results out of clusters of commodity hardware. If you want to look at some primary resources, I tried to pull back some of the papers on the history of Hadoop, some different milestones along the way. But as I said, data centers have really changed. If you look back at 2002, we had a very different set of things to work with. We certainly we weren't looking at having SSDs, for instance. We weren't looking at having really large memory spaces. Gigabit networking certainly was not there. Multi-core processors. None of that would have been, none of that would have been available, but none of it certainly would have been commodity hardware. And so the economics of data centers have changed. Spinny disks haven't changed all that much, actually. Memory is getting much cheaper, but the disks still kind of fail at the same rate and have similar throughput. So in terms of working with MapReduce, there were a couple of limitations that came out right away. We definitely saw this circa, on the Nudge project, circa 2005, 2006. Even before Hadoop was starting to get a name, people were looking at early use cases and seeing that there were a couple things. One is it's difficult to get a lot of people thinking in terms of MapReduce paradigm and writing code directly in a MapReduce API. And I've seen that on my teams before. We've written a lot of Hadoop code directly to MapReduce API, and it was difficult to bring in people and get them to think about complex apps that way. So that's a conceptual level. The other side of it has to do with performance bottlenecks. And you can do a lot in batch, but it may not fit the kind of use case you want. I've seen over the years where people are trying to shrink down batch windows to get closer and closer to streaming in real time. And clearly, there's diminishing returns when you try to shrink batch windows. There's other problems in terms of asymmetries, key value asymmetries, and how processing in MapReduce apps can have bottlenecks. We can go into that in much more detail. But at the end of the day, MapReduce doesn't really compose well for more complex kinds of business logic, more larger kinds of apps. As a result, people spent a lot of time over the past decade building more specialized systems. And really, this comes out of a paper this is redrawn from something that Matei had shown in the last Spark Summit. And there's a great video from, if you didn't catch this, there's a YouTube video that we have up on the Spark Summit site. We started out with MapReduce, great for general batch processing, but then other kinds of specialized systems evolved. And a lot of this sort of followed the pattern of, maybe Google publishing a paper and then other people making an open source implementation, which had happened with MapReduce and Hadoop to begin with. So you see things like Pregel going into Giraffe, or Dremel going into Drill, F1 going into Impala, Millwheel, et cetera. And what that led to was a propensity for a lot of different types of specialized systems, not exactly the same as MapReduce. If you're building apps that combine these, there's a lot of overhead in terms of the ops, the equipment, but also conceptually. A couple of great papers here in terms of history of Spark. Here's a paper from Usenix 2010, really the first formal paper about Spark. And then 2012, the RDD paper, which goes into much more detail about what we're thinking about today as Spark. So the thesis there was to generalize MapReduce, understanding that MapReduce had a couple of problems. Number one, the sort of conceptual bottleneck, if you will, of how difficult it is to express complex logic directly. And then number two, the performance bottlenecks of where you can really get in trouble with complex workflows. Both of those can be resolved to some extent with a couple of changes. And I've seen that in the industry where there's a lot of good cause for using functional programming for big data. We can go into that in more detail. But the two changes that went into place here were to say, number one, fast data sharing, leveraging caches in a very smart way. And number two, having a general graph, a directed acyclic graph to represent the business logic of your app and then be able to have the lazy evaluation on it. So if you put those two together, you get the notion of an RDD as sort of this base abstraction in Spark, the caching and the DAG. And that allows an underlying engine to handle a lot of these different special use cases, all with the same engine, and in many cases with the same code, just with slightly different contexts. So, we see proof in the pudding here where if you compare the code base, it's interesting, just as a metric, to take a look at the amount of lines of code in terms of the MapReduce API for Hadoop, certain number of lines, getting the streaming function out of something like Storm, certain number of lines, looking at SQL implementation like Impala, looking at Giraffe. If you compare that, though, with what's in Spark, just off of the basis of RDDs and all in Spark, and then adding these other libraries for streaming and graph, et cetera, it's about a 7-to-1 ratio in terms of the amount of code. And, putting my engineering director hat on, you see this over time with teams. The more code you have, the more bugs you're going to have to fix, and the more code you're going to have to maintain. So there's a great value to be able to express a wide variety of different use cases, a wide variety of feature sets with Spark as a very general, uniform kind of engine underneath in much less lines of code. So some key points about Spark. This has been covered in a lot of detail. I'm just going to touch on some of the high points. But definitely it handles batch, interactive, real-time, all within a single framework. That should be updated to talk about machine learning and SQL, et cetera. There's native integration with Java, with Python, with Scala, now with SQL, work in progress on R. I heard yesterday about a project involving Clojure. So there's a Clojure DSL as well. I think it's called Flambeau. What this allows is programming at a higher level of abstraction. So we like to think in terms of abstraction layers, where you have this kind of separation of concerns. You're thinking at a higher level of abstraction, expressing your business logic, building your workflows, and then a separation of concerns where Spark is doing the query planning, and the compiler is doing something smart underneath that to obtain a lot more parallelism. That's really where a lot of the functional programming comes in, is to be able to express fairly simple expressions of transformations on your RDDs. That's your business logic. It's easy to troubleshoot, easy for other teams to pick up the code and work with it, but yet it's very powerful in terms of what's happening under the hood. And another thing is that MapReduce is just one set of the supported constructs. There's other types of things that are being done. In the general case, we're talking about the closures being combinators and being able to compose functions together, compose the combinators. This all goes back to like Alonzo Church and lambda calculus back in the 30s. But it's functional programming. A bit more practical, though, the RDDs are, there's really two aspects there. The lineage is being used on the one hand for fault tolerance, on the other hand for parallelism. And ultimately, it gives you this pipelining effect. So, I talked about this briefly before, but the idea is you've got a base RDD that defines where do you get the data from, and then you apply different successive transformations to come up with these other RDDs. Nothing really happens until you have an action that needs to be taken. And by virtue of that, what that means is we've constructed this graph. We've constructed a lineage to express our business logic. And so if one node gets lost out in the cluster, you can pick up the base RDD again from a neighboring node that has a copy of that partition of the data. And then just for that partition of the data, rerun the graph, reevaluate the transforms. And so that gives you fault tolerance. But also built into that is your parallelism, because now you're talking about running this graph on different partitions of data and all running independently. Another thing that it buys is a very nice, graceful degradation between taking advantage of all the RAM you have. If you can fit the working set of what you need to operate on all in memory, great, it will do that. And if you can't, then there'll be evictions. The different partitions in cache are being handled with an LRU, so it will evict the data that's not being referenced. And there's a graceful degradation to the point where you're not using any cache, you're just chunking through the data, doing spills out to local disk. But again, we do this in Hadoop, in MapReduce applications. We do this much more explicitly. With Spark, this is built in at a higher level of abstraction. You can parameterize it too if you want to control it. Okay, that's a lecture that I would have had to get up to the break. And we're at 11:45 right now. Let's see what we've got here. Spark Essentials. Let's go ahead. I'll go through a little bit more of the material. And let's see, whenever we get the lunch delivered, we'll go to that early because I know a lot of people do want to check out. And there's the 1 p.m. Hard stop on that. So if anybody in the back, if one of the TAs, if you could check on, whenever lunch comes, just signal. No, oh, great. Awesome. Awesome. Okay, so let's do a little bit more work here. I will talk a bit about some examples in both Scala and Python. Actually, before I go into this, any questions about sort of the theory of RDDs and how this differentiates from MapReduce? Yeah. That's a really good analogy. The question was, is it like journaling but for tasks? For the computation side, yes, it's very much like that. And you see that, sort of the borderlands on that is when you look at Tachyon and how Tachyon replays. Other questions? Yes? Well, the lineage, that is your graph. So the question is, where is the lineage stored? So on the driver, when you run the app, you're developing that graph. And then that's being serialized out and executed on the cluster. So essentially, the driver side of it is where that's being stored. Somebody knows that this program must be executed. Question?
So does that mean a driver failure is more catastrophic?
Yeah, that's a good point. Where it's starting out from, yeah, a driver would be much more catastrophic than having a worker node. Now, I've seen, depending on the kind of cluster manager, there's ways to get high availability on the jobs that are being submitted. It really depends what type of cluster manager you have. If you're working with Mesos, for instance, and you have a meta framework, then you can have high availability on the executors and then be able to run like Kronos in high availability mode for having no single point of failure on scheduling. So there's some different ways to go about that, but it really depends on what sort of cluster manager. Question?
Somebody asked this before, but I missed it. So what's the difference between like a Hadoop RDD compared to a distributed frame RDD, that kind of stuff?
Great question. So what's the difference between, we've seen different flavors of RDDs. What's the difference between them? There's a notion of an RDD, and there are certain types of functions that can operate on that, and that's in common for all of them. But when we start out with a base RDD, there's a couple different flavors. One is we can say that we take data from a collection. So if it's a collection in Scala, an array of integers. And we could parallelize that into an RDD. Alternatively, we could specify a URL or a path for a file. It could be, it could be something on local disk. It could be out of S3. It could be HDFS, et cetera. But in that case, we're creating the RDD directly out of the file. So those are a couple different flavors. In practice, though, once it's an RDD, you can do the same kinds of transformations on it. We'll see other ones like this, too. Another case would be a schema RDD, where you take the result set from a SQL query, and then that can be operated on as an RDD. Question? Redundant computation, instead of replay. Well, trying to think of good examples for that. I'd love to drill down on that a bit more and figure out. I'll try to come with some good ones for there. But so you're saying the streaming applications virtually all will do recomputation. Okay, like the one-time only semantics off of, say, Spark. For one-time only semantics off of Spark streaming versus what you would do with Storm. Would that be an example, do you mean? Kind of? Oh, CEP kind of stuff. The replay really is, in a way, recomputing, if I'm understanding that right. So it seems like they're analogous. Does the Spark scheduler support? Well, I mean, that'll happen per node. I mean, it'll be happening per partition of data. So it really depends a lot on what's happening out there, whether or not, like if a node gets lost or if there's an eviction. Okay. Am I answering that right? Well, we'll take it offline. Let's catch up a little bit over lunch. Yeah, question. Yeah, we'll catch up on that. Any other questions along these lines here? Okay. Main point there, really 2 points. Number one, MapReduce came out of functional programming, and Spark does as well. Spark is more of a generalization of what you're doing, not just maps and reduces. And number two, this notion of RDD is really the basis of it. And there are two parts of that generalization. One is the caching, and the other is the graph. Alrighty. I'm tempted to say not even go into the next step because we're coming up pretty much on lunch. Anybody know if we've got lunch yet? Oh, another question, yeah. Great question. So how do we compare Spark streaming with Storm? The notion of Storm, you can get the tuples being presented more than once. So one of the benefits on Spark streaming is that you get these one-time only semantics. You know that if you're seeing a piece of data, you're going to see that exactly once. Whereas with Storm, by default, you'd have to manage that. You could put Trident over the top of it or so. Another part where they're distinguished is that with Spark, you can run the same kind of code, business logic, in batch or iterative, interactive, et cetera, but also run it in streaming. So it's nice to be able to have the business logic reuse across different contexts. And I've definitely seen cases for that, where you have a lot of historic data that you want to run some kind of roll-ups on or some kind of analysis, but then you also want to take a look at the most recent results coming off the web servers and then be able to blend the two. So being able to reuse the same business logic in two different contexts is pretty powerful. Does that answer? Okay, good stuff. Any other questions? You know, we're up at like 11:53, so I think that rather than jump into the next part of the material, why don't we just call it good for lunch? And that way, especially if people have to check out, you've got some more time. And we'll re-adjourn here. It's 11:53 now, so let's say we'll come back in about an hour, a little bit over. Sound good? Great. I'll stick around if I can help out, answer with any questions.
grab my USB so that you can copy
It's
it?
downloadable. I had the same question.
Oh, yeah, great. Okay, great. Because that, this may be, yeah, it's a good time to compare and contrast. Disk not ejected correctly. Let's see if I've got it. We had a problem a bit earlier, and I'll find out. Actually, I should check up on these guys and see what they've got. Spark Summit there. What kind of known issues? Ooh, we've got known issues. Huh, I'll have to read that. Here we go. So if you go, they've changed it.
Yeah, okay, but how about slides? Do they have slides available?
Almost, yeah, almost.
No, slides. I checked, slides were not available.
It gets you like,
There was a way to get to them. I saw that last time. I apologize. I'm not. We were doing this track, so I wasn't very sure what the. But if you want to see what the exercise look like, it's all okay.
And are there? But I heard they will post them, but I don't know whether they will post them on this web page or. But they will share the link with that audience, so we can ask them.
Yeah, they'll share. There's a gentleman walking around, Patrick Dono, has a red shirt on.
Oh, he's the one who teaches. Oh no, there are multiple speakers.
Yeah, he's coordinating this.
Okay.
So he's probably the best person to ask about that. I'll try to find out.
Yeah. And so this training is the course that you also offer publicly, right? How about advanced? Is it offered publicly?
We're doing that. We're going to. We do. It's not publicly per se, but we do it in the context of something that had been called AMP Camp. It's now being called Spark Camp. But at Strata, at O'Reilly Strata conferences, we've done that temporarily. I'm very much involved with O'Reilly, and so we'll be doing that in New York, in Barcelona, and wherever. And also, we're building out more of an advanced course program like this, but in other segments. So we'll have more advanced app developer, more advanced from operationalizing, and more advanced from machine learning and data science.
Do you know when approximately it will be available?
I'm probably the right person to ask. I'm definitely that's on my task list. So short answer is we're going to try to get the courses defined before the end of the year.
So you are the one who developed this course, and including this one, and you're also the one who doing training.
I'm training, but the thing is, what we're trying to do is actually make the training materials open source and put them up on, say, GitBooks or something like this, and also eventually take into account the Databricks cloud and incorporate that. But then open it up and have not just a designated trainer going out, but have other organizations that do training to get this to be much broader. So we're actually looking to build partnerships about that.
Okay, another comment I had or question was for this first assignment you used join. Was there a specific reason to use join? Because you can also use count.
We could. I wanted to use join to show the notion of like key value representation and how to be able to compose different RDBs in some sort of product, because it's the number one question that I was hearing in the field. People would learn Spark and come back and say, but how do I do a join? Because the docs don't show me. So I wanted to show that. Having said that, it's a natural segue into showing something like Spark SQL, because you can do the same thing much simpler. But if you understand the mechanism under the hood, it's probably better. Is that?
Yeah, well, the only thing when you're doing join, you probably want to have multiple tuples on one side, multiple tuples. And,
this is a little bit silly thing doing the filter.
Yeah, do the filter and then.
I might have to strip the filter out of there. But
Yeah, maybe.
on the other hand, too, I wanted to make something that was just really straightforward to
Yeah,
troubleshoot.
it's got to be straightforward.
Because we've been hitting, so the back channel on this, I mean, we're actually kind of shocked. We're pleasantly shocked. Every other time that we've done this, we've got almost 150 people in class. I run class sizes usually about 25, 30, and we might spend an hour troubleshooting all the edge cases on Windows. And this time around, we had 2 people raise their hand out of 150, and it went quick. So we're actually moving ahead of what the schedule is. So I don't know if maybe we got lucky, or maybe we just refined the process, but usually getting up to the join is much more painful. Okay. No, I understand. I understand. Where are you heading back to? Oh, very cool. Okay. Are you planning to go to Strata, New York, or if you go to the? Maybe October. Well, there's that too. That's fine. You come during our summer when it's time to wear a jacket. This is unseasonably good. Hi, I'm Mike. Good to meet you.
Actually, I work for it.
Yeah.
In Texas. No, actually, small town in South Texas.
I live in Austin. My wife is up there.
So one of the biggest win-related Spark was Sandra. So one of the things that is provide training.
I want to make sure that we're representing best practices as far as integration, especially when we get into the operational side. But also, for the app developers and data scientists, this comes up very often.
Yeah, so one of the tasks that I'm being developing course, we may be adapting your course. So these are the subjects that will be discussed.
I'm good for some but also Pat is down over this already. So he's overall running.
Okay, yeah, I will see.
There we are. Okay. I'm just tracking the other course. They have some, no big deal here. I was just reviewing on the other course. They were running into some issues. So far, we haven't had this yet. I just want to make sure if there's anything new. Yep. Hi, and grab some lunch.